In this video, I wanted to talk about mathematical functions, how we define them, and what the difference is between what we refer to as a relation. But what we've been working on, a lot in Chapter 2 would be equations in two variables. Like, for example, y is equal to 3x plus 4. We often refer to equations like this as a relation because it's relating x and y based on an equation. And a relation doesn't necessarily just have to be an equation. It could also be given by a graph where you have two things, x and y, and then the graph is displaying the relation between them. Or it can be given by a table of values or just what we call an arrow correspondence chart. But the generic idea of what we call a relation is something where we have what we call a domain and a domain and a range. And those two things are related back to one another. There's a correspondence between them, which is that key idea. And a function is a very specific type of correspondence where for each element of the domain, it has to correspond to one specific element of the range, where a relation doesn't necessarily have to have that specific type of correspondence. And what I wanted to do is look at a couple different examples of functions. We'll start off by just doing a generic example and talking about how we draw an arrow diagram and introduce that. But let's say we're looking at the example from the packet and we're given two sets of things. The domain is stated to be the set 2012, 2013, 2014, 15, 16 through 18. And the range that we're given is the set of Giants, Red Sox, Royals, Cubs, and Astros. And if you're not familiar with these are baseball teams. And what basically the correspondence, there's a correspondence between the domain and range. And the idea of a function is to, well, what is the correspondence in each case? A lot of times the correspondence is defined by a mathematical formula or by a calculation, but in the real world we might have a functional relationship where it's not necessarily given by numbers and mathematical expressions in algebra. But in this case, let's go, one way that we often can visually represent a function is by graphing each set using a blob or a blob diagram, or what we often refer to as a set diagram. But basically, draw each set in a little oval, which is just sort of a representation of a set is just a collection of things, right? And I could visualize them by viewing the domain as a specific set, where the range is a completely different set of things over here. And the relationship highlights the connection between them. And so if you were wondering, well, how are these things connected? If you're a baseball fanatic, you probably know that there's a correspondence between these years and whichever baseball team won the World Series in that year. And now I wouldn't obviously expect you guys to know this without doing it, but it's an example of, well, how do we know a correspondence? A lot of times we might have a formula where an element of the domain would be input into the formula and it would calculate, well, what's the answer? What is the evaluation of the input at the output? Which is the very idea of a function where we have an input, output, and there's always a sense of predictability or understandability with the function. Now, with baseball, we don't necessarily know what will happen until it's happened, but once something has happened, we obviously know the outcome. And so, again, I wouldn't expect you to know this, but in 2012, the Giants won the World Series. In 2013, it was the Red Sox. Now, in 2014, the Giants won again. Now, sometimes you would not be allowed to have a repeated answer as the output value for corresponding to an input value within a function. But in generally, it's fine. You can have repeated output elements within functions. And that's just like in the real world. Sometimes you might have the same outcome that happens multiple different times. Like, obviously, the same team could win the World Series in different years. And then if we continue along this train, actually, I think in 2017, the Red Sox won again. In 2018, it was the Astros. And hopefully, actually, I don't remember who won these off the top of my head. So let's just do a quick Google search to make sure I don't mess up this relationship in the video, because I want to make sure I have it right. Not that it really matters. I think you get the idea. But obviously, we could check to see, well, in what year. And so actually, okay, no, it was in 2018 where the Red Sox won again. And as you can tell, I don't know this off the top of my head. And that's not the important bit again. But basically, we have a certain set of correspondence where, and so that's the idea of the function, itself. And it basically it connects one set of things to another set of things. Now, there are some things that are not allowed in a mathematical function, and that's we're not allowed to have one input value be connected to more than one output value. So let's say, for example, we were like more than one team was allowed to win the World Series. So let's say in 2017, both the Astros and the Dodgers won. And there's a whole lot of controversy about the 2017 World Series due to a lot of cheating that was occurring throughout the regular season. And the Dodgers kind of feel like they had the World Series stolen from them, which again, there's a good argument for that. But at the end of the day, only one team can win the World Series, and you can't really change the record book. In a function, you're not allowed to have two winners, and that's just the way it is. Because there's a key aspect behind this relation where there has to be predictable output. For each input, there is a single correspondent output. And that is a feature within a relation that's not necessarily required. So returning back to, say I had two arrows coming from 2017, one going to the Astros, one going to the Dodgers, that's fine in the general relation, and that's really the only difference between a relation and a function in math. A function has to have only one arrow from each input. It can still have multiple arrows going from two different things into one, but each input has to have a single output. If it's not, if it's not that way, it's not a function. And then just another reason I like this example is because we can talk a little bit about domain and range. Now this, if we're looking at this specific function in the current arrow diagram, this is not the complete picture. Obviously, if we're looking at the list of all World Series champions, we can see that there's quite a few more, right? That if we were to extend the domain back this way, or, technically 2019 has happened. We know who's won the World Series beyond this current domain. But if you catch my drift, we can look at a particular window into this function, but it's not necessarily the full story. And this is the same thing when we're graphing functions. A lot of times we graph functions on a XY graph like that, and we try to see, well, what does the parabola look like, or what does the line look like, or things such as that. We're not necessarily looking at the full relationship that's described by an equation. And a lot of times mathematically, we define relations by a formula, like an equation, y = 3x + 4. And technically this is in function, and the way we change it to function notation is by changing y into what we say is f of x, and we'll talk about that more in the next video. And in math class, that tends to be how we deal with functions and how we think about them. But all that being said, if you look at more values in the domain, it might expand the range as well. Because, for example, maybe in the year 2000, the Yankees won the World Series or something else, we might need to add more within. But one thing that is important is that if there's a value within the domain, it must have an outcome in the range. So say one year baseball was just canceled and there was no World Series, that year we would say is not in the domain. And there's other values that would not be in the domain of this function. For example, let's just say 2011.3, like a decimal value. When it comes to years, there's one winner each year, and it's done using integer whole values, right? We don't use decimal values for years because it's a little bit confusing. So certain types of numbers might not make sense within the domain, or say a fraction, like 7/3. It's like, well, what would the outcome be? It doesn't make sense. So sometimes a function may have integer domain like this. A lot of times with mathematical functions, say for example in y = 3x + 4, there's not necessarily a restriction to what numbers could be plugged into such a formula. And in the next couple videos, I'll talk a lot more about domain and how you figure it out in in a mathematical formulaic function. And it's a little bit different, but the concept is still the same, is that sometimes certain things don't make sense. And we often say that that value is not part of the domain, or it's undefined if it has no outcome. And same thing goes for the range. There are certain values that are within the range, and there might be certain things that are not within the range either. Like in this function, it wouldn't make sense for 2013 to be in the range because we're expecting a baseball team as the winner, right? It wouldn't, a numerical value would not make sense. But in most mathematical functions, both the input and output are both numbers, because it's like a formula where we're taking a number, doing some math to it, and getting another number for x and y. And typically x is the domain value in a function and y is the range. though it's kind of arbitrary and you could reverse it if you needed to, but that's just the prototypical way of doing it. And so there's actually a joke in here that I wanted to lead up to. And if we were to expand the domain of the function, you need to expand the range. Like, say for example, you might want to add in the not the Padres, because they're never going to win the World Series. Actually, they're pretty good this year, but I'm still the skeptical Padres fan who has watched them be bad for many, many years. But for example, the Yankees, they've won the World Series many times, and in order to really see them in the function, well, we need to also expand the range. But we don't always necessarily see everything that's going on in a window. And the whole point about when we look at, say, a graph of a parabola, we can see part of it if we graph it in a calculator by hand, but we don't necessarily see the whole thing because it's all about what are we showing as our domain and range. And with that, it's kind of like for the domain and range, you want to look at, well, what's on your x-axis and what's on your y-axis. Because typically in a graph, a lot of times we'll graph, say, from -10 to 10 as your window for what we look at. And when we do a few on the next couple pages, we'll do some graphing and kind of talk about it then. But my point was that you can find the domain and range of a graph by looking at it and by determining where the function is. But anyways, I'll go ahead and wrap this video up. Key things about function would be the idea of predictability. There has to be an answer. If there's not an answer, it's not part of the function, it's not part of the domain. And that's one of the keys for determining domain of other types of functions, is seeing, well, is there anything that is weird or not allowed, or a value that we have a problem with mathematically? And that's kind of the key for looking at the domain. And for the range is kind of difficult to determine for a function unless you really understand how the function is going to behave. But again, a lot of times a graph, kind of like here, we can make an arrow diagram to help us understand it. In math, we often make a graph of a function to try to help understand, well, where is it? What's happening? What's going on?